Hello, welcome back. Now, we are going to proceed with the second part of Chapter 1, that is on inductor. These are what you should obtain at the end of this video. First, we are going to see the definition of inductor. Any conductor of electric current that has inductive properties can be regarded as an inductor. For example, here we have three types of inductors: an air core inductor, an iron core inductor, and a toroidal inductor. The core type will affect the inductance it generated. What is an inductive property? It is the property that does not like the changes in current. In a way, it will prevent this change by either reducing or increasing the effect, using its induced electromotive force. This is based on Les' law on electromagnetism, that states, an induced electric current flows in a direction, such that the current opposes the change that induced it. Now, we are going to see how the energy is stored in an inductor. In this circuit, when the switch is closed, the current flows through the inductor. This creates the magnetic flux along the coil. It forms a magnetic field within the inductor loop. We use the right hand grip to obtain the direction of magnetic field. This magnetic field is where the energy is actually stored in the inductor. Inductance is defined as the property that opposes the changes in current flowing through the conductor. For solenoid, as shown in this diagram, it depends on several factors, which include the number of turns, the length, the cross-sectional area, and also the permeability of the core. Permeability is analogous to conductivity. It is a measure of the influence of a material on the magnetic flux in the region it occupies. Now, we are going to see the relation between current and voltage across an inductor. For this course, we are using the conventional current flow. Please refer to the symbol of current and voltage across the inductor, that is, the current enters the inductor at the positive terminal, and leaves via the negative terminal. We start with the inductive property of an inductor. When the current passes through it, the induced electromotive force is generated, and its value is defined as V equals L times the derivative of current. If we plot V against the di/dt, the inductance is obtained from its slope. What happens when a constant DC current flows through the inductor? From the voltage expression, we find that the derivative of current is 0. This makes voltage across the inductor is also 0. Hence, we treat the inductor as a short circuit when it is operating under direct current. Next, to find the current expression, we integrate the voltage expression with respect to time and rearrange it. Also note that the current depends on the initial current available in the inductor. In this part, we are going to see the power and energy stored in an inductor. Using the general equation of power, which is a multiplication of current and voltage, the power delivered to an inductor P is given by the current I times the inductance L times the derivative of current I. Meanwhile, from the energy stored definition, we get the energy stored W equals to inductance L times the integration of current. Integrating this from time equals infinity to time equals t, we obtained the energy stored in the inductor W equals to half of inductance times the I square. Bear in mind, there is no energy loss by an ideal inductor. The ideal inductor will return the energy it takes from the circuit. Conversely, in the real inductor, there is a resistive component in it. This will result in power being dissipated by the inductor. Throughout this subject, please note that the ideal inductor will be used, unless otherwise stated. Now, we are going to see the equivalent inductors when they are arranged in series. Let's say we have three inductors in series. To obtain the voltage expression, we apply the Kirchhoff voltage law KVL. After substituting the general expression of voltage across a inductor, and group them accordingly, we can see that the total inductance is similar to that of total resistance in series. Well, what about the equivalent inductors when they are arranged in parallel? Over here, we have three inductors line up in parallel. To obtain the current expression, we apply the Kirchhoff current law KCL. Then, we use the general expression of current across a inductor, and sort them accordingly. Once we do that, we can see that the total inductance is similar to that of total resistance in parallel. Consider a case when there are several inductors connected in a combination of series and parallel as shown in this diagram. To calculate the total inductance, we use the two properties that we have in previous cases. The first one is, we treat series inductors in the same manner as the resistors in series. And the second part is, we treat parallel inductors similar to the resistors in parallel. The equivalent inductors for this circuit is. These are what we can conclude from Chapter 1 contents. The first one, the capacitor uses voltage to store the energy. It is in the form of potential energy, due to the potential difference between the two conductive plates. Meanwhile, the inductor uses current to store energy. This energy is classified as the kinetic energy because the magnetic field is created only when there is a movement of current in the circuit. The second and third, the equivalent capacitance is in opposite manner to the equivalent resistance unlike the equivalent inductance. The fourth one, only half of the energy supplied by a source is stored in either capacitor or inductor, albeit there is no power being dissipated in the ideal inductor or capacitor. This is the end of Chapter 1. I leave you with this quote to ponder. And don't forget that you can achieve anything you set your mind to. Thank you.